Good morning, my dear students. Okay, coming to the second problem, that is what based on minimum potential energy. Okay, so already we studied about the first problem. Okay, it is similar to first problem only. Just we have to analyze the how we are going to assume the diffraction. Okay, in place of delta is equal to how, like that we have to assume means you can solve the problems easily based on this minimum potential energy. Okay, so what do you mean by minimum potential energy? That is what is the potential? That is a combination of what? That is the sum of strain energy plus work potential. We are going to call as strain energy. Okay, so first here we are going to derive the potential energy function equation, then apply the boundary condition, and we are going to differentiate with respect to depending upon the unknown. You are going to get the equations. If you solve means you are going to get the unknown displacement. That is what nodal displacement solution. Okay, so here second problem they given, it is little bit different than the first problem. Okay, though here spring mechanisms consider different, they are fixed. Okay, question given like this for the second problem. Okay, so I am going to solve the second problem here. Okay, for the spring system shown in the below figure, using the principle of minimum potential energy, determine the nodal displacement. Okay, this is the question they may ask here. Okay, so this question is along 12 what 8 to 12 mark question. Okay, so look at here, first you observe the diagram. Okay, so how many springs are there? So here 4 springs are there, that is k1 is k1 k2 and k3 k4. Okay, k1 k2 k3 k4. Okay, so k1 spring stiffness is given 40 newton per mm. Otherwise they may give in the given data. Okay, wherever they want they will give. K1 is equal to 40 newton per mm, K2 is equal to 40 newton per mm, okay, K3 is equal to 80 newton per mm, and K4 is equal to 90 newton per mm. Okay, so here how many forces are? This is what the spring, nothing but what? It is the internal energy, that is the strain energy. Okay, so how many forces are given? We have to analyze how many forces, that is external work. Okay, so here 1 2 3 forces are given, means we have to calculate the 3 displacement. Okay, so force 1 is given here, they are applying here F1 is equal to 60 newton and F2 is equal to 0, they given 0, and F3 is equal to 50 newton. Okay, so once if you know the strain energy and work potential, then you are going to analyze, or you are going to assume the deflection, that is the displacement here. Okay, so here force is given here 1, that is the displacement at node. Okay, if you apply force here, what going to happen? Displacement, it will displace here and here also. Okay, so that delta 1 is equal to what? U1 minus U2. We have to write down here delta 1 is equal to U1 minus U2. Again coming to the delta 2 here, so they given U2 here, force 2. If you apply force here, so delta 2 is equal to what? U2, only one spring displacement takes place. Okay, so coming to the force 3, U3. Okay, if you apply a force U3 here, so what is the deflection? And here also displacement takes place, here also displacement takes place, that is U3 minus U2. Coming to the last, that is force here, the spring force, they given here the force is applying opposite direction. Okay, so consider this force is, it is in it what it is applicable to both the direction delta 3 and delta 4. Okay, so if you apply externally, it is displacement shown opposite, so consider as opposite direction. Okay, that is delta 4 is equal to minus U3. Why it is minus here? So forces is acting opposite to displacement. Okay, so like this you have to analyze, then procedure is same for same. Okay, note down here, we know that work potential is equal to what? Strain energy plus work potential, that is pi is equal to strain energy plus work potential. Strain energy of the spring, this is a standard formula, it is half of k into delta square. So how many springs are there? 4 springs are there, right? K1 K2 in terms of K1 delta 1, K2 delta 2, K3 delta 3, and K4 delta 4. Okay, so just to add all those equation, then let us U1 U2 with a nodal displacement from the figure, displacement changes like this. Okay, delta 1 is equal to U1 minus U2, delta 2 is equal to U2, and delta 3 is equal to U3 minus U2, delta 4 is equal to minus U3. So this is the most important to solve the numerical problems on minimum potential energy. Okay, so I already explained here delta 1, so force 1, if you apply a force here, so displacement here and here, so that is U1 minus U2. Coming to the delta 2, if you apply a force here, only one deflection, that is only one spring displacement takes place, so F2 is equal to delta 2 is equal to U2. Okay, coming to this force 3, so if you apply force, it will display, this spring will displace takes place, and this one, that is U3 minus U2. Okay, so coming to the delta 4, that is force spring, so force is opposite direction, it is pulling this side. Okay, left hand side, so delta 4 is equal to minus U3. Okay, this is if you know means you can solve problem easy. Okay, so now substitute all these values in this equation, total strain energy in the system. Delta 1 is equal to U1 minus U2, delta 2 is equal to U2, delta 3 is equal to U3 minus U2, delta 4 is equal to minus U3. So this is if you substitute, you are going to get like this equation. Okay, so again you resimplify this. Okay, this is a minus b whole square formula, and this is also a minus b whole square formula. Okay, so work potential on the system we have this. Okay, minus F1 U1 minus F3 U3. Here F2 is not there because F2 is equal to 0. So again you resimplify this strain energy. Okay, so here pi is equal to half of K1, this is a square minus b square formula. So okay, just to simplify this, a square plus b square minus 2ab. Okay, here also a square minus b square minus 2ab. Okay, simplify this, you are going to get the potential energy function is equal to final equation this. Okay, that is pi is equal to half of k1 u1 whole square plus u2 whole square minus 2 u1 u2 plus half of k2 u2 whole square plus half of k3 u3 whole square plus u2 whole square minus 2 u3 u2 plus half of k4 u3. Okay, minus the external force minus f1 u1 minus f3 u3, because f2 is equal to 0, so not taken here. Okay, so this potential energy function is to be minimum. So what is the condition? So how many displacements are there here? Okay, 3 are there. Okay, so differentiate one by one. That is, condition is dou pi by dou u1 which is equal to 0, dou pi by dou u2 which is equal to 0, and dou pi by dou u3 which is equal to 0. So differentiate with respect to u1, you are going to get first equation, that is force 1. If you differentiate with respect to u2, you are going to get the in terms of second force. If you displacement u3, if you differentiate u3, you are going to get the third force in terms of third force equations. Okay, so now one by one, dou pi, differentiate the that is potential energy function equation with respect to u1. So we will get like this: dou pi by dou u1 is equal to half of k1 2 u1 minus 2 u2 minus f1. So f1 is equal to, this goes that direction, k1 u1 minus k1 u2. So half of 2 going to cancel, this take common, it will going to get cancelled. So final answer is f1 is equal to k1 u1 minus k2 u2. Again differentiate with respect to u2, that is half of k, that is a into matrix, that is what, k1 2 u2 minus 2 u1 plus 2 k2 u2 plus k3 2 u2 minus 2 u3. Okay, so again this goes that direction, which is equal to 0. So here force is not there, not given, that is f2 is equal to 0. So remaining is just re-simplify this, you are going to get minus k1 u1 minus u2 plus k2 u2 minus k3 u3 k3 into u3 minus u2. So this is in the terms of f2 equation. So give equation number 2. Again differentiate with respect to pi potential energy function. So we are going to get half of into k3 into 2u3 minus 2u2 bracket close plus 2k4 u3, okay, whole bracket close minus f3. Okay, so f3 is equal to what? So this goes that direction. Okay, this is become 0. f3 is equal to minus k3 u2 plus k3 plus k4 u3. So these equations we got in terms of f1 f2 f3. Okay, resolve these equation, solve these equation 1 2 3. So we get okay, rewrite the equation, that is equations. Okay, so we are going to get like this: k1 u1 minus k2 u2 which is equal to f1, okay, minus k1 u1. Okay, again the second equation. Okay, this is the third equation, 1 2 3. Okay, so substitute all these values. So force value is given, k value is given, okay, k value is, f value is given, substitute in the above equations. So you are going to get 40 u1 minus, substitute the in this equation. Okay, 40 u1 minus 40 u2 and minus 40 u1 plus 160 u2 minus 80 u3 and minus 80 u2 plus 170 u3 which is equal to 50. Okay, so on simplification, so we are going to get what, the nodal displacement u1 u2 ut. Okay, take equation, so that simplification I can do, otherwise by using the calculation substitute a1 a2 a3 value. Okay, so you are going to get the displacement values u1 u2 u3 is equal to like this 2.514 and u2 is equal to 1.01 and u3 is equal to 0.771 millimeter. Okay, so like this you have to solve the numerical problems on the minimum potential energy. So here thing is, you have to remember how you are going to consider the deflection values here. Okay, so that is very important here. Okay, so I hope you understand this. Okay, so how to solve this this equation is by using calculation, that is 3 this is a 3 times equation. So substitute a1 value is equal to 40, a2 value is equal to 40, a3 is equal to 0. Again here a1 value, in the calculator you have to feed the a value or a b c value or x y z value. Okay, so here a1 is equal to what, minus 40, a2 160 and a3 is equal to minus 80, minus here u1, that is a1 or x1 equal to 0 and u2 value is equal to minus 80 and u3 value minus 170. If you substitute all these values, that gives the unknown displacement, that is u1 u2 u3. So this is the final answer. Okay, so here once if you calculate u1 means the deflection at u1 here, so it will what, 2.514, displacement at u2 at this place 1.01 and at 3 this place 0.771. okay, so this is the displacement we can calculate it by using minimum potential energy for the given spring mass system. Okay, like this you have to calculate, you have to solve the numerical problems on based on this what, minimum potential energy. Okay, it's very simple to solve numerical problems, but thing is you have to analyze how you are going to consider the deflection at each node. That is very important here. Okay, so once if you understand those, means you can solve the easily. Okay, so first, what is the procedure for solving this? Okay, potential energy is equal to strain energy plus work potential. You calculate the total strain energy on the system and calculate the work potential on the system. Substitute, you are going to get the potential energy function equation. Then you observe in that equation how many displacements are there. Divide, that is what, differentiate with respect to unknown displacement. Suppose 2 means dou pi by dou u1 plus dou pi by dou u2, which is equal to 0. Okay, so again, not plus, equal to 0. Okay, 3 displacement means what? Dou pi by dou u1, which is equal to 0. Differentiate, you are going to get one terms equation. Dou pi by dou u2, again you are going to, which is equal to 0, again you are going to get the one more equation. Dou pi by dou u3 equal to 0, again you will get one equation. So solve all these three equations, you are going to get the displacement. Okay, for your syllabus only maximum of 3 displacement. Okay, u1, u2, u3, not for 4. Okay, so like this is to solve the problems on minimum potential energy function problem. Okay, so I think you understand this. Okay, so thank you.